Most people treat sleep as the negotiable part of the day, the hours that get borrowed when there is more to do, the thing that can be shortened on weekdays and recovered on weekends. The biology of sleep does not support this framing. Sleep is not passive rest. It is the most metabolically active period of the day for the brain, a period during which critical restorative processes occur that cannot happen at any other time, that cannot be compensated for by diet or exercise, and that when chronically shortened produce measurable acceleration of biological aging and increased risk of every major chronic disease. The specific process that makes sleep irreplaceable, the one that no other intervention can replicate, was discovered only in 2013, and it changes the way you should think about the hours you spend unconscious. In 2013, a research team led by Maiken Nedergaard at the University of Rochester published a discovery in the journal Science that fundamentally changed the understanding of what the brain does during sleep. They discovered the glymphatic system. The brain, unlike every other tissue in the body, does not have a conventional lymphatic system for clearing metabolic waste. Lymphatic vessels run through most tissues, collecting the waste products of cellular metabolism and carrying them away for disposal. The brain is separated from the rest of the body by the blood-brain barrier, and conventional lymphatic vessels do not penetrate the brain tissue. What the glymphatic system does instead is use the brain's own vascular system as a clearance pathway. Cerebrospinal fluid, the clear liquid that bathes the brain and spinal cord, is pumped along channels that surround the brain's blood vessels, driven by the pulsation of the vessels themselves. This flow drives cerebrospinal fluid through the spaces between brain cells, where it collects metabolic waste, including the protein fragments that accumulate during normal neuronal activity. The waste-laden cerebrospinal fluid is then exchanged with the venous blood system and carried out of the brain for disposal by the liver and kidneys. The glymphatic system is the brain's waste clearance mechanism, its equivalent of the lymphatic system that clears waste from the rest of the body. The discovery that changed everything was this: glymphatic clearance is almost entirely a sleep phenomenon. During waking hours, glymphatic flow is minimal. During sleep, specifically during deep, slow-wave sleep, the brain's interstitial space expands by approximately 60%, dramatically increasing the channels through which cerebrospinal fluid flows, and glymphatic clearance increases by approximately tenfold compared to the waking state. The brain cleans itself during sleep, and it can only do this effectively during sleep. The waste product that makes this most clinically significant is amyloid beta. Amyloid beta is a protein fragment produced as a normal byproduct of neuronal activity. Under normal conditions, it is cleared from the brain through the glymphatic system during sleep. When glymphatic clearance is efficient, amyloid beta does not accumulate to problematic levels. Amyloid beta that is not cleared aggregates over time into the amyloid plaques that are the defining pathological feature of Alzheimer's disease. The amyloid hypothesis of Alzheimer's disease, the most extensively studied model of the disease's pathophysiology, proposes that the accumulation of amyloid plaques triggers the cascade of neuroinflammation, tau protein tangles, and neuronal death that produces the cognitive decline of the disease. If amyloid clearance depends on glymphatic function, and glymphatic function depends on sleep, then chronic sleep deprivation is a direct mechanism for amyloid accumulation, and therefore a direct contributor to Alzheimer's disease risk. This is not a theoretical proposal, it is documented. Studies measuring amyloid beta in cerebrospinal fluid and in brain tissue have found that even a single night of sleep deprivation produces measurably elevated amyloid beta concentrations compared to normal sleep. One night. One study found that amyloid accumulation in the brain after one night of sleep deprivation was visible on PET imaging, the same imaging used clinically to assess Alzheimer's disease progression. The implication for cumulative sleep deprivation, the years of 6-hour nights that many people normalize as a functional lifestyle, is stark. Years of insufficient glymphatic clearance means years of net amyloid accumulation. The Alzheimer's disease that manifests clinically in the 70s and 80s began accumulating decades earlier in the biology of insufficient sleep. The biological age effects of chronic sleep deprivation extend beyond amyloid accumulation. A large study examining the relationship between sleep duration and epigenetic age, biological age as measured by DNA methylation patterns, found that adults who consistently slept less than 6 hours per night had biological ages approximately 5 to 7 years older than adults of the same chronological age who slept 7 to 8 hours. 5 to 7 years of additional biological aging from sleep duration alone. This is a larger effect size than most dietary interventions and comparable to the biological age difference between sedentary and regularly exercising populations. The mechanisms underlying this accelerated biological aging are multiple. Cortisol is elevated by sleep deprivation. Even partial sleep deprivation produces measurable cortisol elevation the following day, driving the same telomere shortening mechanisms already established in the stress research. Inflammatory cytokines, including IL-6, IL-1 beta, and TNF-alpha, are elevated by sleep deprivation through mechanisms involving both cortisol dysregulation and direct effects of sleep loss on immune cell function. Chronic low-grade inflammation is a central mechanism in biological aging across multiple organ systems. Insulin sensitivity is significantly impaired by sleep deprivation. A study in which healthy volunteers were restricted to 4 hours of sleep per night for 6 nights found that their insulin sensitivity declined to levels comparable to pre-diabetic patients. 6 nights of sleep restriction was sufficient to produce metabolic impairment equivalent to a clinically significant disease state. Growth hormone, the primary hormonal driver of cellular repair and tissue regeneration, is released in its largest daily pulse during the first slow-wave sleep cycle of the night. Shortened sleep reduces the duration of slow-wave sleep and correspondingly reduces growth hormone secretion. Less growth hormone means less cellular repair overnight. The weekend recovery sleep hypothesis, the idea that sleeping longer on weekends compensates for weekday sleep debt, has been specifically studied and has not held up. A study published in Current Biology assigned participants to adequate sleep, sleep restricted to 6 hours on weekdays with unrestricted weekend recovery, or continuous sleep restriction. The recovery sleep group showed some improvement in subjective sleepiness on Monday, but cognitive performance did not recover to baseline. And metabolic markers in the recovery sleep group were not distinguishable from the continuously sleep-restricted group. Weekend recovery sleep does not undo the metabolic, cognitive, and biological age consequences of weekday sleep restriction. The biology does not accept the weekend payment plan. The practical minimum for adequate glymphatic clearance appears to be 7 to 8 hours of actual sleep. The slow-wave sleep that drives glymphatic clearance is concentrated in the first half of the night and is more abundant with longer total sleep duration. Sleeping 6 hours instead of 8 reduces slow-wave sleep disproportionately. The glymphatic clearance effect is reduced more than the proportional reduction in sleep time would suggest. Alcohol specifically deserves mention because its sleep effects are widely misunderstood. Alcohol facilitates sleep onset. People fall asleep faster after drinking. But alcohol suppresses REM sleep in the second half of the night and fragments slow-wave sleep, producing worse biological sleep outcomes despite shorter time to sleep onset. Reduced glymphatic clearance, reduced growth hormone secretion, elevated inflammatory markers. The single most evidence-supported intervention for sleep quality is consistent sleep and wake timing, going to bed and waking at the same time every day, including weekends. Consistent timing anchors the circadian rhythm, which governs the architecture of sleep stages and the effectiveness of the glymphatic clearance cycle. Here is the synthesis. Sleep is not the negotiable part of the day. It is the period during which the glymphatic system clears amyloid beta from the brain, a process 10 times more active during sleep than waking that cannot be replicated by any other intervention. Chronic sleep deprivation accelerates amyloid accumulation, a direct biological mechanism connecting sleep loss to Alzheimer's disease risk. It produces epigenetic aging of 5 to 7 years. It elevates cortisol, drives inflammation, impairs insulin sensitivity to pre-diabetic levels in 6 nights, and reduces growth hormone secretion. Diet and exercise improve health through documented mechanisms. Neither clears amyloid from the brain. Neither compensates for the glymphatic function that only occurs during adequate sleep. Sleep is not where you lose time. It is where your brain performs the maintenance that makes the waking hours possible. If this changed how you think about the hours you borrow from sleep, hit the like button. Share it with someone who treats 6 hours as sufficient. And subscribe for more content like this. See you in the next